Well, let's talk some more about pressure. The kinetic molecular theory actually predicts that gas pressure exists. So pressure is the result of the constant collisions between the particles in the gas and the surfaces around them. This pressure allows us to drink from straws, inflate basketballs, and breathe. We need that gas pressure to be able to breathe. To move air in and out of our lungs, we are utilizing gas pressure. Variations in that pressure, the pressure of the Earth's atmosphere, create wind, and by looking at changes in atmospheric pressure, we can be closer to predicting the weather. Predicting the weather is, in my opinion, more of an art than a science, right? It's a little unpredictable. Did you ever wonder what wind is? Where does it come from? Why does wind start? And how do you even feel wind? Right? You can't feel the air, right? But when the air blows because of wind, then you have increased pressure where it's hitting you and you feel the wind. Most of our weather has to do with pressure changes in the atmosphere, and that causes movement of air and movement of water and causes our weather. So the pressure created by any given gas sample is the force per unit area. So if we wanted to write an equation for that, we could say that the pressure, oh, that's not what I wanted. I was drawing Lewis dots, apparently. Pressure equals the force divided by the area. So the pressure that's exerted by a gas depends on several different factors. One of those factors is how many particles are there. So here we have, these look like two different mason jars, don't they? So this jar has fewer particles in it than this jar does. If we assume, since these jars are next to each other, that they are at the same temperature and that the particles are moving at the same speeds, we would expect this jar to have a higher pressure. Because it's just got more particles in it, they must be colliding with the walls of the jar more frequently than this one. Every collision is a small force. More collisions, more force. And so the pressure is higher with more particles. Does that make sense? I think of gas particles hitting the walls a little bit like a kindergartner hitting you in the shins, right? It doesn't really hurt. But after a while, if you've got a bunch of kindergartners hitting you over and over again, you're going to feel it, right? Each collision of a gas molecule with a surface is pretty inconsequential, right? That amount of force is just negligible. But if you have 50 gazillion of them hitting the wall, now it can become significant. So it's lots of little things adding up to be important. There's another application to real life. When you fly in an airplane, or if you say go up to Grant Grove to visit the big trees, you go up into the mountains, your ears pop, right? And then when you come back down, they have to pop some more. Mine never popped very well on the way back down. Well, what's going on with that? Here's an illustration of what's going on inside your ear. So here's your outer ear, and this is your middle ear, and your inner ear is over here, and there's this eardrum, right? And the eardrum seals off your inner ear from your middle ear. Well, as you go up the mountain, the pressure, there's air inside your head, not all over the place, but inside your inner ear, there's air. That's a gas, it has a pressure. And there is air in your ear canal that's open to the outside. The pressure of this gas will be equal to the gas pressure outside. So if we go up in elevation, the atmospheric pressure decreases. The inside pressure is the same, and this is going to cause your eardrum to bulge outward. That may just feel uncomfortable, Or if you have an ear infection, that could be really, really painful. And this is why babies tend to scream on airplanes, because their eardrums are bulging and it hurts. Well, how do we resolve that? How do we keep our eardrums from bursting? Well, you yawn, you chew gum, right? You have a eustachian tube that connects your inner ear to the inside of your throat, way in the back there. And what happens is, when that eustachian tube opens up a little bit, it lets this air out and lowers the pressure outside, and then your eardrum isn't bulging anymore and you feel better. On the way back down, the opposite process occurs, and you get high pressure on the outside and you've got low pressure on the inside, and you've got to get that eustachian tube to open up again so that the pressure can equalize. That's why chewing gum or yawning helps to open that tube up. If you have a cold, if you're congested or have bad allergies, your eustachian tube is probably kind of clogged up and it's not going to work so well. Well, of course, pressure is a quantity and we have to have units to measure it. There are lots of different units, and we're going to focus on the ones that we use in chemistry. The simplest unit of pressure is the atmosphere. It's abbreviated ATM. It's not an automatic teller machine. It's an atmosphere. That's the average pressure at sea level. The official SI unit of pressure is the Pascal, abbreviated capital PA. That's defined as 1 Newton per square meter. So 1 Pascal is a Newton per square meter. That's a force over an area. So newtons per square meter. We don't use that one in chemistry much at all. The Pascal is a much smaller unit than the atmosphere. 1 atmosphere is 101,325 pascals. Another unit is the millimeter of mercury, which that sounds like a weird unit for pressure, doesn't it? Millimeter is a unit of length, and mercury is an element. How can you have a length of an element be a unit of pressure? Well, this comes back to the original barometers. The original barometer was made by taking a glass tube filled with mercury and inverting it into a dish of mercury. Mercury is a liquid. It's a metal, but it's a liquid at room temperature. It also has a relatively high density. If we made a barometer with water, that tube would have to be over 34 feet tall, because atmospheric pressure can support a column of water that's 34 feet high. When we do this with mercury, though, the atmospheric pressure can only support about 760 millimeters of height. And so they measured the height of the column of mercury in millimeters, and that became a unit of pressure. Normal atmospheric pressure at sea level is 760 millimeters of mercury. You could also measure that length in inches, which is what meteorologists use, 29.92 inches of mercury. So when they say the barometric pressure is 30.05 inches, they mean inches of mercury. If you take this guy, and this is one of the things that early scientists did, if you take this little barometer, it's not actually that little, and you walk up a mountain with it, the height of this column of mercury gets shorter and shorter and shorter as you go higher up the mountain, because atmospheric pressure is less at high elevations. The force of the pressure of the atmosphere pushing down on this is less, and so the column of mercury has a lower height. And as you walk back down the mountain, the column gets taller and taller. If you go below sea level, it'll get above 760 millimeters of mercury. So here's a table summarizing different units of pressure. It's in table 11.1 in your book. It's also in the inside back cover. So here are the units, and these are what they are equivalent to. The way this table is set up, it's not real obvious. All of these things are equal to each other. So 1 atmosphere is equal to that many pascals. It's equal to 760 millimeters of mercury. It's equal to 14.7 psi, or 29.92 inches of mercury. The millimeter of mercury to atmosphere conversion is exact because we defined it that way. 1 atmosphere is defined as 760 millimeters of mercury. And then because millimeters of mercury is kind of a weird unit, they made up a new unit called torr in honor of Torricelli, who was one of the guys who worked on the original barometers, because they thought this would be better than using millimeters of mercury. So 760 torr, 1 torr is exactly the same as a millimeter of mercury. But somehow we use torr, but we have not been able to give up millimeters of mercury. I think because you look at the illustration and it just makes so much sense. So unfortunately, we've got both of them to deal with. I will give you any pressure conversion factors that you need on an exam, but I would suggest to save time that you memorize these. An atmosphere is equal to 760 millimeters of mercury, which is the same as 760 torr. That'll just save you a lot of time. So converting pressure units, same idea as converting other units. We're going to use dimensional analysis. So if we need to convert 1.2 atmospheres to torr, the nice thing about pressure conversions is because of the way this table is set up, we can always do them in one step. So I'm just going to start by writing what I've been given, 1.25 atmospheres. I'm going to have 1 conversion factor, and I want to end up with torr. So that means I'm going to put torr in the numerator and atmospheres in the denominator. Dimensional analysis, we're just using the units to tell us what to do. So I'm going to multiply by torr and divide by atmospheres. Then I go over here and look up the relationship. 1 atmosphere equals 760 torr. So 1 atmosphere in the bottom, 760 torr on top. So then I've got 1.25 times 760 divided by 1. And my calculator is showing me 950 torr. What about sig figs? How many significant figures should the answer have? It should have 3 because I'm starting with 3 here. This is exact. As I've written it, this is ambiguous. And technically, if you're going to be strict about it, would only have 2. So we could fix that in 2 different ways. We could put a decimal point here, or better, we could write it in scientific notation, 9.50 times 10 to the 2 torr. Any questions? Let's do inches of mercury to millimeters of mercury. 30.15 inches of mercury. And I want to convert to millimeters. So I'm going to put millimeters of mercury in the numerator and inches of mercury in the denominator so that my units cancel out. I go over here, 760 millimeters of mercury is equal to 29.92 inches of mercury. So then you get out the calculator, 30.15 times 760 divided by 29.92. Sounds like they're bowling upstairs. 511.831558 millimeters of mercury. How many sig figs should that one have? 4. We started with 4 significant figures. If you're still hating sig figs, most of the time just go with whatever you started with. This was 4, so go with 4 at the end. The 760 is exact. The 29.92 has 4 sig figs, and so this should have 4. If you're still having trouble rounding numbers, that is something you need to work on. I've been grading some worksheets, and I'm seeing some very interesting things. Yes? You didn't get that? What'd I do wrong? Oh, I did 2015. I did 20.15. Why? Because I hit the wrong button. How about 765? Okay. So, and there's another illustration of why you should do the calculation twice. Also on the worksheets, I'm seeing that some people have the problem all set up correctly. All the numbers, all the units, beautiful. And I don't know what happened with the calculator, but you got the wrong answer. Is that better? 765.8. Any questions? Here's another one. Convert a pressure of 173 inches of mercury into pounds per square inch. The table isn't given. The relationship isn't given in the problem. In the homework, you have to go look it up somewhere. On an exam, you need to go look for the conversion at the beginning or by the periodic table. So we're going to look it up. We're going to go back here. Here we have inches of mercury, and PSI is pounds per square inch. So it's 14.7 and 29.92. So I'm going to write that down. 29.92 inches of mercury is equal to 14.7 PSI. That's the relationship I need. I wrote it down because otherwise I'll forget. So again, pressure conversions can be done in one step. 173 inches of mercury. I'm going to PSI, so I'm going to multiply by PSI. I'm going to divide by inches of mercury. This is the relationship. You have to keep the numbers with their units. Let's see if I can get this one correct. 173 times 14.7 divided by 29.92. 84 something? Yeah, good. Blah, blah, blah. Bunch of digits. How many sig figs? 3. We started with 3. 14.7 is not exact. That has 3, this has 4. So 3 sig figs. What do we round this to? 85.0. I want to keep the 10th digit. So I look at the next one, it's 9, I have to round up. Rounding a 9 up makes it a 10. So that's going to be a 0 here, and there's my decimal point. And then that's going to round the 4 up to a 5, and the 8 gets left alone. We need the 0 because otherwise we don't have 3 sig figs. PSI. Any questions?